Hi, I'm Ed Begley Jr., and I'd like to tell you about an exciting new renewable energy technology. Altarock Energy is conducting the Newberry Volcano Enhanced Geothermal Systems Demonstration in the Deschutes National Forest in Central Oregon. First, I'd like to tell you a little about the history of geothermal energy and how this new technology, enhanced geothermal systems, can dramatically increase the use of geothermal energy and help secure our nation's energy independence. Geothermal energy, the Earth's own heat, could help solve today's energy challenges. Geothermal power generation dates back to 1904, when at the Larderello geothermal field in Italy, electricity was generated from geothermal energy for the first time. Geothermal energy is already being used today for domestic heating and electricity production, providing clean, renewable baseload power. It could contribute to a sustainable energy future for the United States and around the world. Geothermal power represents an essentially unlimited resource we can more fully develop and dynamically change our energy future. So what do we need to do to take advantage of this tremendous resource potential? Naturally occurring geothermal systems, called hydrothermal reservoirs, are only found where heat and open fractures filled with water can be accessed at relatively shallow depths, like in the western U.S. and around the Ring of Fire. What if we could create ideal geothermal conditions almost anywhere? That's exactly what Enhanced Geothermal Systems, or EGS, proposes to do. To help us fully understand EGS, let's first look at how a natural hydrothermal system works. In a naturally occurring hydrothermal system, groundwater is heated by underlying magma or by circulation through deep faults or fissures. Production wells, drilled into the Earth's surface, tap into the hot fluid of these naturally occurring hydrothermal reservoirs. Under pressure, heated fluid flows up these production wells to the surface and into a power plant. Geothermal energy gives us a reliable flow of renewable baseload power with minimal environmental impact. Remember though, naturally occurring geothermal does have its limitations. It can only be used where underground reservoirs naturally exist, mostly in the western United States. EGS, however, can be created almost anywhere. By creating a water-filled fracture network in hot rock, we can make a geothermal reservoir. EGS could be a viable solution to the energy challenges facing us today and to the creation of a new energy economy. Let's look at a current EGS project, the Newberry EGS Demonstration, being conducted by Altarock in the Deschutes National Forest in Central Oregon. In Phase 1, a team of scientists and engineers review existing data about the Newberry EGS demonstration site, conduct baseline measurements, develop plans, and obtain permits for Phase 2 operations. In Phase 2, we will create an EGS reservoir around an existing well, over 10,000 feet deep, using Altarock's proprietary methods and technology. By injecting water at high pressure, we will open or stimulate existing natural fractures using a process called hydro-shearing. Clean, cold groundwater, produced from an existing on-site shallow water well, is pumped at high pressure deep into the injection well, where the temperature is over 600 degrees Fahrenheit. When the cold water reaches the hot, dry rock surrounding the well bore, the injection pressure causes the existing natural fractures to open and fill with water. This process is continued until cracks are opened to a distance of about 1,500 feet, or 500 meters, around the well bore. When the first fracture system has grown to the desired size, a biodegradable, non-toxic material called a diverter is injected with the water to temporarily block fluid flow into the newly opened fractures. The diverter forms a shield around the well bore in the first set of fractures, so more fractures can be opened deeper in the well bore. As the diverter begins to block the first set of fractures, continued water injection causes a second fracture system to open, followed by a second injection of diverter, shielding the second fracture system from further stimulation. We use this to control the size of the reservoir as it forms. A third cold water injection creates the final fracture system, and the stimulation process is complete. At this point, the water injection is stopped and the injected water begins to reheat. As the water heats, the biodegradable diverter begins to dissolve, allowing the fractures to open and the water to flow through the entire fracture network. The hydro-shearing process and opening of cracks creates movement and sound in the rock, resulting in microseismicity. The opening and growth of fractures during stimulation is mapped by real-time measurement of this microseismicity. Using a microseismic array and AltaStim, AltaRock's sophisticated proprietary modeling software, we can closely monitor the process. We'll map the fracture network and generate a microseismic event map around the wellbore, showing us the size, location, and orientation of the fracture system. With all this information, we know where to drill the production wells into the fracture network. Conventional well drilling techniques are used to directionally drill production wells into the newly created EGS reservoir. Precision-guided directional drilling allows us to penetrate the greatest number of open fractures for maximum well productivity. Cold water can now be pumped down the injection well, flowing through the newly created EGS fracture network, absorbing heat and flowing up and out of the production wells, creating hot water or steam to generate electricity or provide domestic heating. In Phase 3 of the Newberry EGS demonstration, we summarize the collected information to develop a conceptual model of a commercial-scale EGS system, including the most cost-effective way to create an EGS reservoir, the performance that can be expected, the number of wells required, and the best type of power generation technology to use, either flash or binary. While not part of the Newberry EGS demonstration, electricity can be generated from geothermal energy using one of two power cycles, flash or binary. In a flash system, steam is separated from hot water in a pressurized vessel. In a binary system, the hot water is used to boil a working fluid, often isopentane. In both systems, the heated fluid is then used to turn the turbine and generator. Flash systems typically use wet cooling systems that consume relatively large amounts of fresh water, while binary systems often use air cooling, which consume no water and have low visual impact. In either system, any remaining liquid is recycled back into the geothermal reservoir. The steam in a flash system, or working fluid in a binary system, turns the generator, producing electricity that is delivered to the national electric grid and on to consumers. EGS is a renewable process that's environmentally friendly, generates tax revenue and family wage jobs at home, and will help to ensure our national energy independence. EGS, the future of geothermal energy.